In this last video of chapter 13, we're going to round up some kind of leftover ideas, and the first one is the use of Diels-Alder in a multi-step synthesis. So most problems do not just outright say, use Diels-Alder to synthesize this product, but this one does. It says that we are using a diene and a dienophile. So the first thing that we want to do is analyze our molecule and see if we can figure out anything just right off the bat. So first, what you probably notice is that the product is all cis. All four of the methyl groups are pointing in the same direction. So this tells us that our dienophile must be cis because the dienophile is going to be retained. And both of these substituents on the diene must be outside, because what we have is these guys on the same side, and the endo form is going to be our major product, right? So in endo, the electron withdrawing groups of the dienophile ends up on the same side as the outside groups. So we want our diene to be substituted on the outside. The other thing that we need to think about is that if we want to get the endo product, which we do because that's going to give us the best chance of having like a successful synthesis, we must have electron withdrawing groups on the dienophile. Now, looking at our product, our dienophile is going to be made up of these four pieces here. These are methyl groups. These are electron donating groups. So we're going to have to do something in order to change this, because methyl groups are electron donating, they're not electron withdrawing. This is not going to encourage the formation of an all cis product. So our last question here is really, how do we get a methyl group from an electron withdrawing group? And these are going to make up the non-Diels-Alder steps of this synthesis. So we need to figure out the identity of this thing, but something that we've already figured out is the identity of our diene. Our diene has to be made up of these 6 carbons. We know that we want our methyl substituents to be outside. So we have already identified our diene. What we don't know yet is the identity of our electron withdrawing groups. But we're really close. We know that we need them to end up as methyls, right? So we're going to draw this out on a blank slide so that we have plenty of space. So what we want to think about is, how can we create these all methyl situations from an electron withdrawing group? Now, usually in a synthesis, working backwards is the best way. And in this one, that might not actually be the case, because what we need to do is start off with something specific and see if we can work our way down to a methyl. Now, one of the things that could be helpful here is that we know that we don't want any extra carbons. We only want these carbons here. And you actually don't know that many ways to make an alkane. One of the ways that you do know to make an alkane, you actually learned just last chapter, is to take an alkyl halide and react it with lithium aluminum hydride. Now by doing that, you can displace the halogens and you would end up with your alkane. And it shouldn't do anything else to the rest of your molecule. That's the other kind of tricky thing here, is that you have to make sure that you don't ruin the rest of your molecule. For your electron withdrawing groups, since you don't want any extra carbons, one of the best options could be a carboxylic acid. But even if you didn't know that yet, you could kind of keep working your way back. You don't know that many ways to make alkyl halides. You know that you're not going to be starting with this. As your starting material, so we know that this is not an option here. So one of your better options could be to take an alcohol and react with PBr3, phosphorus tribromide, and get to the alkyl halide. Now, let's say that you did go ahead and pick a carboxylic acid as your first example, which again, you may not have known, you may not have thought of this initially, but by doing this practice problem, I'm kind of planting this idea in your head. This is a good electron withdrawing group to start with, and you can always kind of start with whatever, and if you can't get to the product, go back and change your electron withdrawing group. But when you heat this up, you'll end up with a Diels-Alder adduct where you have these methyl groups pointing down, and you have your carboxylic acids pointing down. This would be your major product. Is there a way to get from carboxylic acid to alcohol? Yeah, we learned it last chapter, right? You can take lithium aluminum hydride followed by an aqueous acid workup, and you would get to your primary alcohol. So this synthesis is kind of a difficult one, definitely. Trying to get from carboxylic acids to methyls, and also knowing that you had to do that in order to get the endo product, that is multi-level thinking. But since we did this one together and you're able to watch this and you're able to re-watch it, this can kind of plant the seeds in your head so that next time you approach a synthesis problem that's going to go through Diels-Alder, you kind of know the different things that you need to consider, right? You need to consider, are my dienophile substitutions pointing in the same direction as my diene substitutions? Is my diene cis or trans? Is my dienophile cis or trans? If my dienophile does not have electron withdrawing groups on it, I need to figure out how to make those electron withdrawing groups, right? So this is just a pathway that you kind of can have in your head now, and you can borrow pieces from it essentially. So a couple of reminders about synthesis problems. Backwards is often easier because there are usually fewer options for how to start. Usually you only know a couple ways to make the product's functional group, but when you look at your starting materials, usually they are very malleable. You look at your starting material and you go, oh crap, I know so many reactions that I can do with this, but the product, it's usually only one or two ways that you can make that functional group. Like making an alkane, you only know one reaction for that really at this point. So that's a pretty good sign that you could start backwards. You also need to analyze which bonds need to be made and which ones are going to be broken. That can point you in the right direction of chemistry. If I hadn't said, use a diene and a dienophile to make this product, having the cyclohexene as the major backbone is a huge hint that it's a Diels-Alder reaction. And always, 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 when you're doing a synthesis, compare the chemical formulas. Figure out what changed from the reactants to the product. A lot of times students miss that the product has one extra carbon in a place, or they don't properly count up their degrees of unsaturation, and you just end up doing the wrong chemistry because you didn't really think about what was changing. So always do some chemical accounting at every step. Now, the last topic in this chapter is UV-Vis spectrophotometry. We're not going to go into too much detail on this. You do learn about UV-Vis spectrophotometry in Gen Chem 2 lab, so you've already kind of been exposed to this. What you haven't been exposed to is the applications in the organic field. So remember that UV-Vis spectrophotometry uses Beer's law. So absorption is equal to the molar absorptivity times the concentration of the sample times the path length. You have to be careful about your units. Path length is sometimes in decimeters, sometimes it's in centimeter, depending on how your molar absorptivity is expressed. The molar absorptivity is the intensity of absorbance at a given wavelength. So this is a value that actually goes with the compound. It can be determined experimentally. Typically, alkenes absorb energy at wavelengths below 200 nanometers. Conjugated multiple bonds tend to have absorption at higher values. So note, ethene absorbs at around 171 nanometers. Butadiene absorbs at 217, and then the more conjugated the system, the higher that value gets. And the reason that is that the gap between the highest occupied molecular orbital and the lowest unoccupied molecular orbital is shrinking. So the ability to absorb UV-Vis light depends on the ability to excite an electron from the HOMO to the LUMO. And the smaller that gap is, the higher wavelengths of light are going to be absorbed. Your textbook on top hat actually has a really interesting example using sunscreen molecules. So the molecules that appear in sunscreen are highly conjugated because the entire purpose of them is to absorb that UV energy so that your skin isn't taking it in. It's not that it actually, prevents the UV energy from touching you. It's that the sunscreen molecules are actually taking the brunt of it. They are absorbing that UV energy. They are getting destroyed by the UV energy, which is why you eventually have to reapply. So even if you're, not swimming or something, it's not water that's doing most of the removing of your sunblock or damaging the sunblock. It's actually the light itself. Your textbook also talks to you about different dye molecules and why molecules appear as different colors. So it's a really fascinating example.